Consider the temperature right now, 72 degrees Fahrenheit, 22 degrees Celsius, 295 Kelvin, 3 different numbers, and all of them are correct. The absolute value is arbitrary. Only the difference between two temperatures drives heat flow. Linear algebra proves why this must be the case, and it starts with a simple graph. A single matrix is null space, and a vector of all ones will show us why only differences ever matter. Here's our network. 4 nodes labeled 1 through 4, connected by 5 directed edges. Edge E1 runs from node 1 to node 2. Edge E2 runs from node 2 to node 3. Edge E3 runs from node 1 to node 3. Edge E4 runs from node 1 to node 4. And edge E5 runs from node 3 to node 4. The arrow on each edge is a sign convention. It defines which direction we call positive. Flip an arrow and you only flip a sign. The underlying physics stays the same. This graph could represent an electrical circuit, a pipe network, or a bridge truss. Now let's translate this picture into a matrix, 1 row for each edge. The incidence matrix is a matrix that records which nodes each edge connects. It has 1 row per edge and 1 column per node. For our graph, that means 5 rows and 4 columns. Let's build it row by row. Start with edge E1, which runs from node 1 to node 2. We place -1 in column 1 because that's the from node, and +1 in column 2 because that's the to node. Columns 3 and 4 get zeros. So row 1 reads -1, 1, 0, 0. Next, edge E2 goes from node 2 to node 3. This gives us row 2, 0, -1, 1, 0. The -1 sits in column 2, the from node, and the +1 sits in column 3, the to node. Finally, for this frame, edge E3 goes from node 1 to node 3. That gives us row 3, -1, 0, 1, 0. The -1 is in column 1 and the +1 is in column 3. Rows 4 and 5 will be filled in next. Edge E4 runs from node 1 to node 4. Following our convention, we place -1 in column 1 and +1 in column 4, giving us the row -1, 0, 0, 1. Edge E5 runs from node 3 to node 4. So we place -1 in column 3 and +1 in column 4, giving us 0, 0, -1, 1. Now we have the complete 5x4 incidence matrix A. Let's look at it all together. Notice the pattern. Every single row has exactly 1 -1 and 1 +1, with everything else being 0. Out of 20 total entries, only 10 are non-zero. This makes A a sparse matrix, meaning most of its entries are 0. That sparsity directly reflects the structure of the graph. Each edge connects just 2 of the 4 nodes, so each row only needs 2 non-zero entries. We've encoded the graph. Now let's see what this matrix does when it acts on a vector. Assign potentials x1, x2, x3, x4 to the 4 nodes. We want to compute A times x. Row 1 of A is -1, 1, 0, 0. The dot product with our vector gives -1 times x1 plus 1 times x2, which simplifies to x2 minus x1. The potential difference across edge E1. Row 2 is 0, -1, 1, 0. This gives -1 times x2 plus 1 times x3, which equals x3 minus x2, the difference across edge E2. Row 3 is -1, 0, 1, 0. This gives -1 times x1 plus 1 times x3, which equals x3 minus x1, the difference across edge E3. Row 4 is -1, 0, 0, 1. This gives -1 times x1 plus 1 times x4, which equals x4 minus x1, the difference across edge E4. Row 5 is 0, 0, -1, 1. And this gives -1 times x3 plus 1 times x4, which equals x4 minus x3, the difference across edge E5. Putting it all together, A times x equals the vector, x2 minus x1, x3 minus x2, x3 minus x1, x4 minus x1, x4 minus x3. Every single entry is a difference of potentials across one edge. This reveals the true nature of A. It is a discrete difference operator, the linear algebra version of subtraction. We know what A does. The next step is to determine what A fails to detect. The null space, the set of all vectors x, where ax equals the zero vector, tells us exactly that. Setting ax equal to 0 means every edge difference must vanish. From the 5 rows of A, we get 5 equations. Equation 1, x2 minus x1 equals 0. Equation 2, x3 minus x2 equals 0. Equation 3, x3 minus x1 equals 0. Equation 4, x4 minus x1 equals 0. Equation 5, x4 minus x3 equals 0. From equation 1, x2 equals x1. From equation 2, x3 equals x2, which already equals x1. From equation 4, x4 equals x1. So all 4 variables must be equal. x1 equals x2 equals x3 equals x4. Call that common value c. The solution is x equals c times the vector 1, 1, 1, 1. The null space is one-dimensional, spanned by the all ones vector. Picture 4 potential bars, 1 per node, all at the same height. Slide them all up together and every difference stays 0. A uniform shift is completely invisible to the incidence matrix. This connects directly to the temperature analogy. Celsius sets 0 at water's freezing point. Kelvin sets 0 at absolute 0, which is a shift of 273 degrees. Yet the difference between boiling and freezing is 100 in both scales. In Celsius, 100 minus 0 equals 100. In Kelvin, 373 minus 273 equals 100. The additive constant cancels in every subtraction. That constant is the null space direction, 1 degree of freedom that no difference measurement can ever detect. On the right, we see the algebraic connection. Choosing a temperature scale is the same as choosing a constant c. The null space, spanned by the vector 1, 1, 1, 1, represents exactly this freedom. The rank of A, the number of independent columns, equals n minus 1, which is 4 minus 1, giving us 3. One dimension is consumed by the null space. Finally, if we sum all the columns of A, we get the 0 vector, confirming that the columns are linearly dependent. Engineers resolve this ambiguity by grounding, fixing one node's potential to 0, like choosing sea level for altitude. Let's see what happens. On the left, we have the situation before grounding. We have our 4-node graph, the full 5x4 incidence matrix A, with a null space equal to the span of the vector 1, 1, 1, 1. The rank is 3, and there are n equals 4 columns. Now, set x1 equal to 0 and remove column 1 from A. This gives us the right panel. After grounding node 1, node 1 is marked with a ground symbol, and the matrix A is reduced to a 5x3 matrix, keeping only the columns for nodes 2, 3, and 4. The null space collapses to just the 0 vector. The rank remains 3, and now it equals the number of columns. By the rank nullity theorem, 3 plus 0 equals 3, so the system is fully determined. Notice that the rank stays at 3 in both cases, but the null space dimension drops from 1 to 0. Grounding is not a hack. It is choosing a reference point, the same way Celsius chooses the freezing point of water as its 0. The incidence matrix is actually the first stage of a 3-stage pipeline for network analysis. Let me walk you through each stage. Stage 1, we multiply by A to get edge differences from node potentials. E equals A times X. This is the difference operator, and it's what we've been building today. Stage 2, we apply a conductance or material law to convert those differences into flows. Y equals C times E. In the context of electrical circuits, this is Ohm's law. The matrix C encodes the conductances on each edge. Stage 3, we multiply by A transpose to enforce conservation at each node. A transpose times Y equals F. This is Kirchhoff's current law, which says the total flow in and out of every node must balance. So the full pipeline is difference operator, then constitutive law, then conservation law. Today's video builds stage 1. We constructed the incidence matrix A and understood how it computes edge differences. The rest of the pipeline follows the same linear algebra framework. Let's wrap up with 3 key ideas from today's lesson. First, every directed graph encodes as a sparse incidence matrix with one -1 and one +1 per row. The graph structure maps directly to the matrix structure. Second, multiplying by A computes differences across edges. In other words, the incidence matrix is discrete differentiation. A times x gives us the vector of edge differences, x2 minus x1, x3 minus x2, x3 minus x1, x4 minus x1, and x4 minus x3. Third, the null space of A is spanned by the all ones vector 1, 1, 1, 1. This single algebraic fact proves that only differences carry physical meaning. Absolute potentials contain one free parameter that no edge measurement can ever pin down. Next time someone states a voltage or a potential without naming a reference, remember, the null space of the incidence matrix is linear algebra's way of saying that number is incomplete.